Hello, and thank you for joining us. Today's webinar is Get Your Mercury Lab Started with today's Thermal Decomposition Mercury Analyzer. Our presenter today is Jeff Forsberg, Mercury Technical Manager for Teledyne Leeman Labs. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Jeff Forsberg.
Hi, everybody. Thanks for joining today's webinar on the Hydra 2C. Some of the basics of the system will be covered today, the software, how we develop some methods and some tips on some maintenance and so forth. So the Hydra 2C is designed for US EPA 7473, and then a couple of ASTM methods, 6722 and 7623. 6722 is for coal and coal byproducts, and 7623 is for petroleum and light petroleum samples. And 7473 is solids and solutions, just about any major seeds. So the detection limits on this system, they're superior to liquid digest. It has a nominal detection limit of approximately 0.001 nanogram. So if we look at that 0.001 nanogram and use the mass of the sample that we're putting into the system, they're far superior to anything you can do by aqueous digest. So for example, if we have a 2-gram sample and we divide that into 0.001 for our nominal nanogram detection limit, that becomes 0.005 nanogram per gram, or ppb. And if we use a 0.5 gram sample, that becomes 0.002. So if we're to equate that to liquid, the liquid equivalent would be 0.05 and 0.02 ppb or ppt nanogram per liter in solution. That's really super hard to do. So by default, now the Hydra 2C is far superior to getting down to the absolute lowest level of detection in your sample. How does it work? So it's atomic absorption. There's 7 steps. So we load, inject, dry, combust, purify, remove moisture, collect, elute, and detect. So up here are the 7 steps. So you have a carrier gas, you put the sample in the boat, it goes into the drying combustion oven. Then from there, it travels through the catalyst zone where some of the spectator ions, such as chlorine and your sulfur and so forth, are taken out. And then we remove the moisture in an Nafion dryer. Then it collects on the gold trap, and we heat the gold trap and elutes, and it goes through the spectrometer. The spectrometer light source travels through a mirrored long cell. That path is 10 inches, and then it goes through a short cell, 1 inch, and then it's determined at the detector. Deep well photovoltaic detection system. Typical range is 0.5 to about 1,500 nanograms. You don't need sample pretreatment. Combust the sample to create elemental mercury, Hg0, and then that collects on a gold trap. So no stannous, no sodium borohydride, and the light source is 253.652. So the use of 2 cells will give us a wider dynamic range for determination of mercury, and the system will automatically pick the long path or the short path cell depending on the response or the microabsorbance units in that sample. Here I'm showing a 1 nanogram per gram at a 0.5 ml sample. So nice peak. Here's the sensitive, and this is the least sensitive cell here. So it's direct determination of mercury at trace levels in solids or semi-solids. Low determination, low levels of mercury, ppb levels in liquid samples, aqueous samples. Although it's not recommended for a lot of liquid aqueous type samples, if the majority of your sample set are liquid, then this is really not the system for you. But if you have, 75% of your samples are semi-solids or solids, and you're not digesting to create an aqueous sample, and 25% of the samples you have are liquid type samples, then it might be a good fit. Direct determination of petroleum and petroleum distillates. There's no time-consuming complex digestion for the samples. No wet chemistry unless you're running aqueous samples and they're acidified. So if they're acidified to preserve the mercury, then we need to add L-cysteine. That's a thiol group, and that will, in theory, it grabs the mercury and keeps it in solution so it don't off-gas. One of the problems with the acidified sample in the nickel boat is nickel and will produce hydrogen via the reaction with the acid. So when the hydrogen is produced, in theory, it can grab some of the mercury and off-gas that out of the sample, and thus giving you a bias flow result for that. And then this system also eliminates toxic waste disposal, because basically you just have ash, and I theoretically just dump it in the waste bucket. When is it useful? So a thermal decomposition or a combustion atomic absorption system is useful if you have just about any sample that you can get into that boat. Where soil, sediment, sludges, fly ash, fish, food and feedstocks, plant and tissues, ores, and then petroleum products, crude and distillates as well, and then difficult to digest samples. There's a few samples that we can't run. Maybe a sample that's some type of ore, so forth, and it needs a really, really high combustion temperature to off-gas any component within the structure. In that case, once it's ground, you're going to basically get anything that's attached to the surface of that compound. So there's two paths to success for the Hydra 2C. One is straight up combustion atomic absorption, and the other one is combustion atomic absorption with a VHC mode. VHC mode is for petroleums and petroleum distillates and volatiles. The CAA mode is for samples that have high auto-ignition temperatures. So when you're injecting it into the hot zone or the combustion and dry zone, they won't auto-ignite as they're going into the furnace. Within the software, I think it's extremely friendly and easy to navigate. So there's three tabs. You have method, sequence, and analysis tab. And with those, when you navigate between each of those tabs, on the drop-down menu, method, view, run, and tool and help. So the view, run, and tool and help doesn't change. It stays the same for each sub-tab. So on the tabs down here, when we go to method, sequence, and analysis, and view, run, and tool stays the same. Most of your activity is going to happen in the method and the sequence, and then the analysis is where you view the results. So under view and run, view, you can search all chapters, latest chapter and date range. Run, you can run a single standard, quality control standard, sample, sequence, run a stat sample or something that needs to be immediately ran. And then you can do drop is standard gem sample. Navigate the tool and systems. Kind of important. Most users put this right on that guide this system through some day-to-day activity. You can do ramp temperature, so ramp up to combustion temperature, on dryer temperature, and with just a splash screen. Here, this is check the alignment of the movable parts, and you have some instrument diameter. This is where you can, that's going to be generated standard things like change user and so forth. And you can also navigate here. This is some global settings. Here, down over here, you can change your drying temperature and time, catalyst temperature, and your wait time. The wait time here for the catalyst is the time that when it allows you to traverse through the naphthalene dewatering or the moisture and collect on the gold trap. So typically that could be anywhere from 30 to 60 seconds, depending on temp, catalyst temp, lamp on and off, and amalgamator temp. This is all global settings. And then down menu for method, we have renamed say clone. Clone is nice. So if you have a group of that are all uniform in matrices, but you might have to tweak something a little bit. So you can just clone it, give it its new name, and then you're going to have the calibration and everything in there, and then the parameters for the samples will be automatic into the sequence. But there's no worries here because you can adjust the sequence parameters for each individual sample. So in the sequence, here, the tab down here for sequence, up on the top now for the drop down and say print exit, some basic stuff. Here you, on these little tools here, you have cut, copy, paste, auto renumber, fill down, and then this little button over here is your enter control. So it'll go, when you enter, it'll go left or it'll go down depending on which mode it's in. And then when you're over here, you can right click and start from a certain position on a rack that's loaded up with samples if you want to stop it and then start again. And that's how you would do that. But there's a quick note on that. So it's going to reset the auto sampler. So you have to move it behind its staging pins if you're going to restart it in a certain sample. If there's more than one rack on the auto sampler, if there's only one rack, you don't have to worry about it. I mentioned earlier that you can customize your samples. So in the sequence tab, when you create your sequence, you have all these controls up here. Dry temp, dry time, decomp temp, decomp time, wait time, and elute time. That's for the gold trap. You can adjust this, but the the gold trap temperature is global. If you set it, for example, at 700 degrees C, it's going to be the same for each sample. But the other parameters are fully customizable within the sequence itself. And here under sample type, you have your calibration standard, unknown, which is your basic sample that you don't know what's in it. QC, continuing QC, QC stop, preload, and update slope. Within the sequence, also you have something called preload. So this is used for samples that are extremely low in concentration, and if you would really like to see something. So you can click on preload and then do as many as you want. It's not limited. And then you put the weight in for each preload sample. And then when you think you have enough or you're satisfied with what you've loaded onto the auto sampler, right below the last preload, you actually put the sample name and weight of that one too. And then it's going to combust each sample and load it onto the gold trap. And at the end of this sequence of events, it will heat up the gold trap. So all of the samples are now added onto the gold trap. It's going to heat the gold trap. The mercury is going to go off to the spectrometer, and then it's going to give you a response or a microabsorbance. And it's going to take that and divide it by the sum of all the masses and then give you your concentration. But I have to caution all users that since this is a gold trap system, and we have mercury everywhere, and you can be as cautious as you want, you're still going to have small amounts of contamination. So you're going to wear gloves, you're going to keep your boats clean. But since it's an additive process, the more boats you add into the system, the cleaner it could be. So I try to limit it to three preloads with one gold trap on up to the spectrometer. So that's some of your limits, but you don't have to put as many as you want. So if you're in a super clean, like in the on the bench. Over on the analysis bottom, you have support. You can show this is the raw data. You can export a CSV file of the raw data, and then you can print this scan of the sample. So you click on the sample, it shows that sample. You click on the chapter, and then you look at your results, and you can click here, and you can arrow down, and it will give you different, or click over here, and it'll give you different peaks for each sample, so you can look at your data from the data set itself. When you get into show data, it's the data points, the time, the raw intensity, the microabsorbance. So it's the full scan of a single sample from start to finish. You're going to have your baselines and peak microabsorbance regions, peak absorbance, and then your corrected peak values, the microabsorbance values from both cells. So if you scan up to the top, you're going to see these values up here. So if you want to take and do things with data offline and on an Excel spreadsheet, create graphs and charts and different things like that, this is how one of the ways you could do it, by exporting that data. In the report section, right up here on the analysis tab, you have 29 selectable fields, detailed and long-term statistics for the sample set. It's kind of nice to pick and choose what you want to report and what you don't want to report. Under recalculation, you can do a weight change, say, oh, I really put the wrong weight in the sample, which in all honesty, should never happen. You should be more in control of your samples and your analytical processes and so forth. So you should have the correct weight, but things can happen if you need to change a weight, and you can justify that weight change based on your data from your notebook or whatever. All you do is click on a sample, click on the weight and put the new weight in and recalculate. So this is a sample. This is the data you get when you click on one sample when you're here. It gives you some basic data, the moisture, integration time, and decomp temperature, and some of that data in there. But that's how you would do that. On the analysis tab also, if you click on rename, so reports, you can exclude single samples or exclude all. You can rename sample or samples. Click on the chapter to access this, to rename it, and then you also have a name history. So you click on the chapter, you go to rename, and you can rename the sample. And again, this is if you would happen to make a mistake. On the software, we have the favorites bar. You can do most of the things you need to do for start, stop, and so forth from right here. You can run a standard, run a check standard, run a sample by itself. You start your sequence. Once you've started it, you can pause it, run that stat sample, your user login, sample search, your audit trail. Startup, this is important because when you enter into the software, you click on this, it'll start the gas flows, start all your heaters for the predetermined set temperature from your method, and that'd be from your global settings here, and then sleep. At the end of the run, you can click over here and have it go to sleep. It will look for a cool down temperature. I have mine set to 150 degrees C. That's the temperature of the catalyst oven. Once it hits that, it's going to go ahead and turn the gases off inside the instrument, and it's going to put it in sleep mode, close the injector, and so forth. This is really important because it preserves the integrity of the catalyst. So if you stop your system and you leave your injector open, it's hot, and then when you start to cool down, that catalyst and combustion and dry zone can be contaminated. So I like to preserve that. And it's also a nice, easy way to cool down the catalyst because the injector is closed. You've got gas flowing. Your heaters turn off. It cools down at a nice controlled rate. So it's a nice thing to do to protect your system and so forth with the Hydra 2C. So some of the basic operating conditions that you would want to start with: drying time, temperature of 150, could be 60 seconds. If your samples are somewhat moist, probably less than 10%, you reduce that quite a bit down to maybe 30 seconds. Catalyst, basic starting point for the catalyst temperatures: 600 degrees with the wait time, again, the time to get to the gold trap, 30 seconds, 180 seconds on the combustion, and 800 degrees C for that. It will typically take about 45 to 60 seconds to get up to your combustion temperature, and then you like to hold it for 60 to 90 seconds to ensure you have a nice robust combustion of that sample to elute all the mercury out of that sample and into the catalyst and traverse through your moisture removal setup and then on to your gold trap. So these are some of your basic conditions that you would put into the global setting under your method tab, and then the user interface that opens up when you click on that. You need to follow really good GLP. So while you're making standards and handling boats and so forth, because this is a collection system, so any contamination that's in and around the area is going to get collected on that gold trap, so it's all additive. If you're running a liquid system, a standard cold vapor atomic absorption spectrometer, which is continuous flow, small amounts of contamination, you wouldn't even notice them. But in this system, small amounts of contamination are going to get collected on the gold trap. In the air, they can be on dust particulates, and they can drop on to the sample itself and then get loaded into the system. So again, GLP keeps your dust cover down on the system to keep particulates from landing in your boats prior to analysis. Intermediate standard calibration. So what I do is I have 1,000 ppm stock standard, and I do serial dilutions from 100 ppm down to 1 ppm, 0.001 ppm, I should say, or 1 ppb. So 1 to 10 dilutions. So here's the percent acid by doing that. And I start with 1% here, and then I keep the 1% all the way across. And then so it's additive from my original acid, which was actually 12% right here listed. So that's why these lower as you go. So you need at least 1%. I don't like to keep anything higher than that or less than that in the standards to preserve them. We don't put hydrochloric acid in these standards, only nitric, and they're not very well preserved at low concentrations of acid. So at best, these standards are only good for a few days, the lower level ones, and you have to remake them. So how does this thing work? Well, it's all mass-based. So you created those standards. Like here is a 1 nanogram sample. So you're just going to vary the weight for the standard and put it in the boat. So for example, to have a 0.1 nanogram, I'm going to use the 1 ppb or the 0.001 ppm and 100 microliters of that. And then when that goes to the gold trap and gets into the system, it's 0.1 nanogram mass. To get a 600 nanogram mass, I'm going to use the 10 ppm, and I will use 60 microliters of that sample, and then that's 600 nanograms. So you just vary the weight of the standards you created and load them into the sequence. Before you do that, it's nice to get the system started. So how do we start it up? I like to wake up the catalyst with 100 milligrams of flour. That's a polysaccharide, so it's lots of carbons. It will get the catalyst excited, get everything going, get all the surfaces ready to go, so it's ready for your samples. After that, I do 100 microliters of water, and then I run an empty position. And I just do them from the favorites menu, hit run sample, put the bolt right onto the forks, and let it go. If you're running volatile samples or petroleum distillates, you should put diatomaceous earth in the boat. That will preserve some of the sample and or crushed alumina. This is for volatile samples. So it does improve the integrity during long wait times. And you can run experiments too. You can put earth in, not put earth in, run a set of 3 samples of a particular matrices and do it over time, say at time 0, 1 hour, and maybe 2 hours or 3 hours, and see how it varies. If you end up with decreased microabsorbance or response for that sample, then you know that you're losing mercury. The boats are going to dry up if you have a small amount of liquid in there. Over time, they will dry, but the mercury should or may not be there, and this is a good way to tell if your method is going to need some type of substrate to preserve that mercury in that boat. So now you know how to create your intermediates, how the system works on mass space, how do we get our standards entered. So you navigate over the tools, and I mentioned earlier about the standards library, so this is important. Here you're going to come in here, you're going to add a standard. This UI will pop up. You give it the standard name, concentration. If you need lot number and date open and so forth, you can put that in. And once you create all that, it's going to show up in the standards file right here. And then close is just an autosave. It's there. Now from that point, now you have them entered. Earlier I showed in the sequence where you have your sample type. So here you click on calibration standard. And once you click on that, then in the ID, when you have the drop-down menu, all the standards you just created are going to be in here. You pick them, you change your sample weight to match your nanogram that you want for that standard spot, and then you just press go, hit go, and it's going to run it. So in this case, I'm using 0.001 ppm or 1 ppb, and my weight is 0.1 or 100 microliters and 500 microliters. So that's going to give me the 0.1 and 0.5 nanogram. And then once you have it all entered and you've looked at it and you're satisfied with the weights, then all you do is click update and it'll load it on the sequence. I typically do run a 14 point calibration within both cells, but you don't have to. If all your samples are less than 20 nanograms, then you could put multiple points between 0 and 30 nanograms and only run in the sensitive cell if that's what you want to do. Low range calibration, typically 20 or up to 30 nanograms, linear. Pick and choose calibration points. You can have multiple points at the same mass. You can select or deselect points. It's all right in here. It's really easy to do. But one of the ways I like to run the system is I like to include the 50 nanogram sample in the sensitive and run quadratic. Some of them might improve. It just depends on what your technique is. So for example, here the 20 went from 19.8 down to 19.9. The 10 got a little bit better, but some of the lower calibrations, they shifted a little, but if we look at the 0.5, it went from 0.408 to 0.453, which is better. So that's just the way I like to do it. You don't have to do it that way, but I like to run that 50. And the high range, typically up to 1,500 or 1,000 nanograms. In this case, I'm running 1,000 nanograms. You're going to run quadratic. Again, same thing. You can choose multiple points at the same mass, or you can select or deselect points. If you want to take standards in or out of the calibration, here's a little tip that I do. I like to include the blank. So I'll select the blank, add it to this calibration. So it did change it a little bit on this one. So the 50 went from basically 59 to 49. The 100 didn't change a whole lot, went down a little bit. When we get into the higher masses, you don't see a significant change in predicted concentration based on the response of those, but the 100 was off a little bit. But it is a good technique to include that blank. It does seem to dial in a little bit more. Anyway, that's the way I like to run it. So again, the calibration, you could accept a single pointer, accept all. You can add points, delete points. You can clear the calibration. If the calibration is horrible and you just want to start over, work on your GLP, you can delete the whole calibration. You can also print the graph. When you start to look at running samples, it's good to know your sample, know what you're putting into the system. So in a lot of cases, you're putting fuel into an oven, so you're going to create a mini explosion or a combustion of that sample. So you should Google that matrix and kind of look for a typical assay of that matrix type. It'll tell you what your weight should be, maybe some things that you might want to change, and temperature, ramp time, moisture time, and so forth to run the system. So you know, if it's higher low concentrations, you may be able to increase or decrease your weight to fit it into the analytical range. You should also avoid components, large concentrations, percents of components that may harm the catalyst, such as halogen, your sulfur compounds, even your organic sulfur. You can run up to about 8% sulfur without doing a lot of damage to the system, to the catalyst. It will consume it, but that's a pretty good percent sulfur. So it's not too much of a concern for most samples. Moisture, you should determine the moisture so you know how to run your temperature and your time for moisture removal of that sample. And then physical. Will the sample be contained in the boat? Is it light, fluffy, feathers, ash, dust, that type of stuff? Is it homogeneous? That's really important. So you can check that by running 2 or 3 samples of the same sample set and see what kind of results you get. And also you can just inspect it and look at it as well. For volatiles and petroleum distillates, you can't go above 80 milligrams of sample. Otherwise, that explosion inside the combustion zone can damage the catalyst tube. It actually can crack the quartz tube. So yes to aqueous samples, but with limitations. I say less than 500 mils for sure, 500 microliters a sample. But typical would be 50 to 100 microliters a sample. But again, if that's all you have is liquid samples, this is not the system for you. But when we run aqueous samples, I like to run the external dryer. This is magnesium perchlorate. It goes in between the combustion module and the spectrometer, so it'll remove the moisture that happens to slip through the Nafion. It'll keep it out of the spectrometer. Moisture has a lot of absorbance wavelengths, and around 253 is one of them, so it can disrupt the baseline slightly and give you some bias low or bias high results, just depending on what's happening in the cells. So get rid of the moisture, and again, if you have a lot of samples that are liquid, it's probably not the system for you. Volatile samples, VHC, we have VHC mode. I talked about that a little bit. Methyl mercury, there's an extraction method where we can get methyl mercury samples in like tissue and so forth. And then some novel techniques like thermal desorption are also possible, so we can look at different species, inorganic species of mercury within the system. With the aqueous sample, I ran a study from 100 to 1,000 microliters and 1 to 42 samples, and which takes a long time, about 6-7 minutes per sample to get the moisture out of the system. And basically there was no disruption of the baseline during the 42 samples from the low sample to the high sample. So the external moisture drying system works very well for moisture removal and to keep it out of the spectrometer, so we don't have baseline disruptions and or false positives at the extreme low level. VHC, so what is that? It stands for volatile hydrocarbons. Our full acronym is CAA-VHC. The software is going to manage the injection temperature. The injection zone, when the sample goes into the combustion tube, it's actually about 36 degrees C on the inside. The thermocouple is going to say it's 50. The thermocouple is on the outside, so there's a small offset there. But it's mitigation of auto ignition during the injection. So if you have an extremely volatile sample and it's got a low auto injection temperature, say, less than 100 degrees C or 75, in theory, when it hits that hot zone going through the opening into the catalyst compartment, it could explode. Then you'd lose your sample. And again, weights of less than 80 milligrams per sample. So when you're in VHC mode, the user interface is the same as standard mode with the exception of the drying. The drying can't change. That's hard-coded at 150 degrees C for 60 seconds. And that's to bring it through kind of a light touch through its auto ignition and let it explode at a low temperature, and then you can go into the combustion. So less violent in theory, but it probably doesn't change the violence of the combustion of that sample. But again, less than 80 milligrams of that volatile sample will help preserve the system by itself. Method and all that, none of that changes. Sequence is exactly the same. You can, with the exception of the dry time and dry temperature. So here is non-VHC. In VHC mode, it's hard-coded in. You cannot adjust it. So all of this is exactly the same with the exception of dry temperature and dry time. You can't change that. VHC mode, our partner in the Netherlands was involved in an interlaboratory study, performance study on volatiles, naphtha. They achieved 26.9 and 26.5 on 2 samples that were sent to the laboratories. I think there was over 30 laboratories. The mean was 27.9, 28.1, and with their report, their Zeek score was minus 0.14 and minus 0.2. They actually, I saw the data out of all the laboratories, their results were the best or the closest to the mean of the entire group that was involved in this study. So the VHC mode worked really, really well. Methyl mercury, so there's a novel method produced or written by Korea. It is law 9.1.9.2, law 2, and it's extraction for methyl mercury out of any food sample where the concentration has been set. And the principles of the application are a weight is pretreated with sodium chloride and hydrochloric acid and toluene, and then we centrifuge it, and then we take the toluene and we extract the mercury from that fraction into L-cysteine, and then that's the fraction we load into the system. So you push the pipette through the toluene layer and extract 100 microliters of the L-cysteine sample, and you load in that onto the boat, and then you run it. The application note release for this is AN 2102, and I'm also using an external dryer, which is AN application note AN 1701. And then you quantitate the methyl mercury based on total mercury in that injection. And it's pretty simple. So you have each sample must have a dry weight on it. So you run a % moisture, so you know what that is. And then you take A times B divided by C times 1.075. So in the Hydra C, the results are in nanogram per gram, which is ppb. So that's a direct conversion to micrograms per liter, also ppb. So thus the results become microgram per liter. So then I'm going to run an extraction blank. You have to have a control blank. So I subtract that. So that's the A is equal to the results minus the blank. And then the extraction volume. So the sample that I used for the extraction was 5 milliliters. So that's why divided by 0.005 to get it to liters. And then you just divide by the dry weight, C, and then multiply by the conversion to methyl mercury. So it's atomic weight conversion of organic to, or I should say inorganic to organic methyl mercury is 1.075. And that gives you your value of methyl mercury in that sample. So here is BCR 463, which is methyl mercury in tuna fish. ran 7 extractions. I achieved 2.81 for a concentration that's 92.4%. And along with this, I'm running some quality control. This is bovine muscle tissue, 91.4%, marine sediment, 104% recovery. And then the BCR also has a total mercury in that, and 25.87, and with the moisture corrected, 28.99 or 102%, and then coal fly ash at 101%. So lots of different sample types on the system all at once, again, because it's mass-based. Validation of the system. So EPA 7473 is solids and solutions. So here's my solution, is a residual fuel oil at 3.94 plus or minus 0.18. The certification value is 3.46 plus or minus 0.74. So got it. And then the solids, coal fly ash at 105 plus or minus 22. And I achieved 103% recovery on that one. So that's validation for the EPA method. For the coal method, in this sample, I ran the 1633, and again, so that validates the 6722. And then validation for the ASTM oil method is the residual fuel oil by itself. So again, one method with your quality control checks and your samples basically validated 3 different methods of analytical methods, one from EPA and 2 from ASTM on one run. Maintenance really easy on this system. So we have the maintenance tab, and you have counters for when to replace it, and you have videos and documents that open up and walk you through how to perform the maintenance step by step. For example, for changing the catalyst, it's super easy. So there's a captive thumb screw. You open it up. This injector module will open up. It'll swing over to the left, and then a couple of thumb screws, and you can move your catalyst and put a new catalyst in. It literally takes less than 1 minute. If it's cool, hot, I've taken them out hot and put them on a surface that can handle the temperature, wearing gloves that can handle the temperature as well, so you don't burn your hands. And then changing or working with the cells in the spectrometer, it's pretty easy. You just, another door, you just flip it up, and then you have access to those cells. For the catalyst tube, about 500 samples or greater. I've achieved as much as 1,000 samples before. It depends on your matrices. Gold trap, 1,000 samples, could be higher. And again, you're going to be running quality control samples, so you're going to know when a certain component is going to start to fail. So if you exceed your timer, and if your results are still good, then I certainly wouldn't take anything apart and fix it. But you got to keep in mind that it potentially could start to degrade in the middle of the run. So if you're uncertain and you want 100% assurity it's going to be okay, then go ahead and change or replace that component. For the Nafion dryer and gold trap, it's pretty easy. This auto sampler portion here, this whole thing will slide forward, and then you have access to a couple of thumb screws up here, and then you can remove your module, and then from there you can exchange your Nafion dryer or pop your gold trap out and just put it back in. It's really that easy. Takes about 30 minutes or so. For the non-experienced, for the experienced person, maybe 15 minutes to change the Nafion. Just a couple of minutes to change the gold trap, and you're on the way. When it comes time to cleaning the cells and cell windows, so you want to use spectrophotometric IPA, isopropyl alcohol, cotton swabs and or foam swabs, You're going to have disposable beakers, powder-free gloves, and purity wipes, or lab disposal wipes. Might need them all. And you take it apart and set it on a clean surface ready to work. And a little trick is to keep your windows and parts orientation the same. So left side, right side, front and back cell, etc. So you know how to put it back together. Don't mix and match them up. So if you have an issue with the cells and you clean them, when you put them back in, you'll see the results. But if you're changing windows and stuff around, it throws a little bit of unknown in there, so you may not be able to keep everything in control like you would like to. So pour a small amount of isopropyl alcohol into beaker, and again, wear gloves when you're handling the cells, cell windows and caps. You got to wear those gloves, keep it in control. You're going to use IPA, wash the inside with a wetted swab, and then you can dry it with a cotton swab, and then you want to blow out the fuzzies. And you can use the gas right off the back of the instrument, the carrier gas. Turn your pressure down, maybe 5 psi. When you need to blow out the fuzzies, just turn it on, blow them out. Same process for the cell windows. IPA, dry flush. Be careful so it doesn't fly out of your hand. It's a small optical window. And then immediately after cleaning these windows, you assemble them back into the complete cell again. So that's why you clean the cell first, so they're ready to receive the clean windows. You don't have to set them back down. It goes right back onto the cell assembly. And then place them back into the Hydra tube C, so they're ready to go for the next analysis. So in summary, the analyzers are applicable to your direct combustion methods, NECAA, combustion atomic absorption method. You have superior detection limits for solids and semi-solids. Can be as low as 0.001 nanogram. It just depends on how clean your boats are, how clean your laboratory is, and your GLP, whether you can get that low or not. They're easily adaptable for analysis of extractions, as I presented the methyl mercury extraction. And one thing I didn't talk about or present the data, but they're also adaptable to exotic analysis, such as thermal desorption experiments. So you can have different dry temperatures, the combustion temperature set to 400, and run just a single second combustion time, so it really doesn't affect it. And then you use the change in drying temperature to elute different fractions of mercury species, such as mercury sulfide, elemental mercury, mercury chloride, and so forth out of the solid sample. And you can change the dry temperature and then reanalyze that same sample, leave it in the boat, and then let it run through again. It takes about an hour to run through all of your your dry sequences for one sample to get all your rough numbers. So it's not quantitative analysis, but it's qualitative. So it'll give you a good perspective of what might be in that sample. And then that data can be used for different research. So depending on what the starting mercury, how it's locked up in a compound, will affect the modeling from inorganic over to methyl mercury or a different organic mercury. So you can model cleanup and prevention of contamination out in the environment. So with that said, my contact information, mobile phone is 402-709-2752, and then my email is jeff.forsberg@teledyne.com. So I'd like to thank everybody for joining the webinar today, and I hope you get at least a good introduction to how the system works and how easy it is to manipulate the software to make it do what you want to do and to run your sample. So if you have any questions, go ahead and please submit them through the webinar, or you can email me directly, and I'll get them answered as soon as possible. So again, enjoy your morning, afternoon, or evening, wherever you may be watching from, and have a great rest of your day.